We continue with chapter 1, which is analysis of stress. Previously, you already learned how to calculate the internal resultant forces. Now, we will learn how to calculate the stress. The stress is from the internal resultant forces that you calculate, and then you can convert it into stress. Let's take a look at the learning outcome. By the end of this chapter, you should be able to identify and explain the concepts of stresses, apply the concepts of stresses in calculating the normal and shear stress, analyze the average stress acting over the bar cross-section area, describe the single and double shear stresses, thus calculate the average shear stress. Calculate the allowable stress by applying the safety factors. From the learning outcome, you can see that you have two types of stress, which is normal stress and shear stress. Normal stress, you get it from normal force. Remember the normal force that you calculate in internal resultant loadings or internal resultant forces. This normal force you will convert it into stress. And then shear stress, as you will get it from shear force. And then stated here that there are two types of shear stress, which is single shear and double shear. Shear force, you have two types, single and double. Now, let's move on to the next slide. It states that the bolts used for the connection of this steel framework are subjected to stress. This bolt is said to be subjected to stress. Why? All the elements or all the structure is subjected to a stress because they need to hold the structure together. Okay, so the structure itself has a responsibility to hold the structure together. What happens if these bolts are not in stress? And then it becomes loose, and if the bolt is loose, then the structure will collapse. So that's why everything need to be in stress, because they need to hold the structure together. Stress. When a body is subjected to an external load in section, there is a distribution of force acting over the section area which holds each segment of the body in equilibrium. The intensity of this internal force at a point in a body is referred to as a stress. Stress is defined as force per unit area that the force acts upon. When you section, means that you cut the elements or you cut the structure. There is a distribution of forces acting inside the elements because they need to hold the element together. So this intensity, the distribution of the force, we call it as a stress. Stress here is defined as a force per unit area. Stress is equal to force per unit area, force over area. Force, you will get it from internal resultant loadings that we previously learned. This is simply described as the intensity of internal force. If you look at this, when you cut the segment, so you can see the intensity of the forces acting around the cross-section area. This intensity is to hold the structure together. The general state of stress, a cut of cubic volume element can represent the state of stress acting around the chosen point. The magnitude of these components depends upon the type of loading and also the orientation. Every structure that you need to design, it depends on the application. When you know the application of some structures, then you can determine the type of loadings and also the orientation of the force. Normal stress. The most fundamental type of stress exists is the normal stress. It indicates by the lower Greek letter, which is sigma. Normal stress acting perpendicular or normal to the cross-section area, given to you by this equation. Here it states that the normal stress is the most fundamental stress that every engineer need to know. This is the symbol for normal stress, which is sigma. And the normal stress acting perpendicular to the cross-section area, the formula give to you sigma normal stress is equal to F, which is a force divided by area, or if you use normal force and divide by area. The average normal stress in axially loaded bar when a cross-section area bar is subjected to axial force through the sine rod, it's only subjected to normal stress. It is assumed to be average over the area. So when you cut the elements, when you section the element, then you can see the intensity or the distribution of the forces. But what we calculate is we calculate the average normal stress. This is the formula. Sigma stress is equal to P over A, or sigma is equal to F over A, or sigma is equal to N over A. N is a normal force, F is a force, P is a load. Same thing. So this is what it means by the average normal stress. This is your element, for example a bar. Then when you section this bar, then you can see the distribution of the forces or the normal force. Then we calculate the average. We assume that all the distribution are in the same phase. Mathematically, we express as a stress, sigma is equal to force divided by area. The unit for force is Newton or kilonewton. The unit for area is meter square or mm square. Then you will have this unit for stress. We simplified to megapascal. There are two equilibrium state of stresses, which is in tensile or in compressive stress. For tensile stress, one that tend to stretch the member and pull the material apart. This is how the tensile stress acting. It will pull the material. When it pull the material, what happened to this one? It become elongates. So that's why if you see here, the tensile stress is positive because it elongates. How about compressive stress? Compressive stress is one that tends to crush the material of the load carrying member and to shorten the member itself. So it tends to push the material and then the material become shortened. So when it shortened, that's why it is negative, because it shortened. Let's take a look at example 1.1. The bar has a constant width of 35 mm and a thickness of 10 mm. Determine the maximum average normal stress in the bar when it is subjected to a loading as shown. The question asks you to calculate the maximum average normal stress. the question already give you this bar cross section area. Then from that you can calculate the area. For this question, you can see that there is a 12 kN at point A, 9 and 9 kN at point B, 4 and 4 kN at point C, and D 22 kN applied load. How to calculate the average normal stress is by section the area. So you section between AB, between BC, between CD. When you section, you expose the internal forces. When you have the internal forces, then you can calculate the stress. So first you need to section. Section or cut the segment. Second, expose the internal forces. And then calculate the stress. For when you expose the internal forces, please make sure you follow the sign convention. Remember the sign convention? If you cut from left, then everything goes to the right is positive. For normal force, if you cut from right, everything goes to left, positive. Now you cut the section. Now you know that you need to section the area, so we draw the free body diagram for each section. Section AB. When you cut section AB, you can see point A here. They have 12 kN applied load. When you expose, you will have the internal forces. I name it as NAB. Why it goes to the right? Because I start from the left. And then by using equilibrium equation, summation Fx is equal to 0. To the right is positive. Then you have negative 12 plus NAB is equal to 0. NAB is equal to 12 kN. Then we do the same for BC. When you draw the free body diagram for BC, you need to start from A. You cannot take only the BC cross section because the structure need to be in equilibrium. If you just take free body diagram for BC only, then your structure or your elements are not in equilibrium. This is point A, 12 kN applied load. Point B here you have 2, 9. Then please don't change the diagram. And then when you section, when you cut, you expose the internal forces. I name it as NBC. How to calculate NBC? Same, by using equilibrium equation. Summation Fx is equal to 0. To the right is positive. Why I use summation Fx? Because all the forces are in x direction. Negative 12 minus 9 plus NBC is equal to 0. Then NBC is equal to 30 kN. Okay, you do for CD. When you do CD, you will get NCD is equal to 22 kN. From this value, internal forces AB, internal forces BC, and internal forces CD, which one is the maximum value? if you look at the question asks you to calculate the maximum average normal stress. Stress is equal to N over A. You know that A is equal to 0.035 times 0.01. How did I get this value from the question? And then N maximum, you know that it will occur at BC. 30 kilonewton, convert kilonewton, 10 power of 3 divided by area, 0.035 times 0.01. The maximum normal stress is equal to to 85.714 megapascal at segment BC. This is your final answer. Please try this exercise. Read the question. Determine the largest internal normal force in the bar, thus determine the maximum normal stress of the bar. This question is same as a previous example. Point A, point B, C, D and F. But now you have connection at F. The previous example you don't have any connection, but now you have connection at F. This one also same. You need to calculate the internal forces between AB, BC, CD and DF. Since at point F is connected, then you need to start from A. You need to start from free end if you have another end is connected. You need to start from A and then follow the sign convention. If you start from the right, everything should go to the left. Positive. Do the same steps. Calculate the internal forces. And calculate the stress for each segment and then determine the maximum. For this question, the maximum will be 88.419 megapascal at segment. Please determine the segment. And then please check your answer with mine. This is my answer. Please check it. For this example, the casting is made of steel, has a density of 7,850 kg per meter cube. Determine the average compressive stress acting at point A and point B. So now they give you the density. You need to know how to convert density into force. Please take a look at the unit, kilogram per meter cube. So you need to times watt, you need to times watt to cancel out the meter cube. Okay, this is the solution. Your answer will be 61.607. For this exercise, determine the average normal stress in rod AB if the load has a mass of 50 kg. The diameter of the rod AB is 8 mm. The rod, this is the rod. So what are the shape of the cross section? It is a circle. You need to know how to calculate the area for circle. You can use pi r square or pi d square divided by 4. The question gives you a diameter. If you like to use pi r square, please make sure you convert the diameter to radius. And also the question gives you a mass, 50 kilogram. You need to know how to convert kilogram to kilonewton. This one is 50 kilogram. For this question, A is pin and B is pin. So if it is pin, you can just solve the internal forces. This one I label it as a FBA, and here is FCA. How did I know the direction? I assume. Now you draw the free body diagram. This is point A, and you have internal forces of FCA and internal forces of FBA, and also the 50 kilogram. Why it is downward? Because of gravity. Convert it to kilonewton. For FCA, it is a inclined load, so you need to resolve to x and y direction. And then by using equilibrium equation, summation Fy is equal to 0, summation Fx is equal to 0, or summation moment is equal to 0, then you can have the FCA and FBA value. And then after that, FBA value, and then convert it to stress. Convert it into stress by stress is equal to F divided by area. You see that you only have two unknown. No, you just use two equilibrium equation. You need to decide which equilibrium equation is suitable to solve this question. Now we move to the next stress, which is shear stress. Just now we've learned about the normal stress. Now it's a shear stress. Shear stress is the intensity of force or force per unit area. Shear stress at parallel or tangent to the cross section of the load carrying member. The symbol is tau. It is also force per unit area because it also a stress, but now it's acting parallel. Just now normal stress acting perpendicular, shear stress acting parallel. The symbol is tau. This is the formula. Tau or shear stress is equal to F over A or V over A, whereas V is equal to shear force. Remember the shear force that you calculated in the previous subchapter, internal resultant loadings? That shear, you need to convert it into shear stress. Same as normal stress, shear stress also we calculate an average shear stress. Average shear stress distributed over each section area that's developed a shear force. If you cut this section, then you can see that this is the distribution of the forces, and then we calculate the average. Mathematically, it's expressed like this. Shear stress is equal to V over A, whereas V is equal to internal resultant shear force. A is the area. As I mentioned earlier, there are two types of shear stress, which is single shear and double shear. Single shear is a force between two plates. This is where the shear occurs. Then you have the formula. Single shear stress is equal to V divided by A, the same formula. one force is here, and then to make it equilibrium, then you have another V here. Double shear is the force between three plates. Okay, here this part and this part, you will have a shear force. This is V. To make this structure in equilibrium, then this one will be V divided by 2, then V divided by 2. The formula here will be tau is equal to V over 2 divided by area, and then you manipulate the equation, then you get tau shear stress is equal to V divided by 2A. This is a formula for single shear, and this is a formula for double shear. Same goes to this one. This is the same explanation. You can use V, you can use P, or you can use F. This is a comparison between normal stress and shear stress. Normal stress acting perpendicular. This is your area, and this is a perpendicular force or perpendicular stress. This is a perpendicular. While shear stress acting parallel. This is your area, and this is a parallel. Take a look at this example. The inclined member is subjected to a compressive force of 3000 Newton. Determine the average compressive stress along the smooth area contact defined by AB and BC, and the average shear stress along the horizontal plane defined by EDB. For this one, you need to know which one is the contact area that the question asks. You need to calculate the compressive stress for AB and BC. Where is your AB? This is your AB. This is your BC. And for shear, the question asks you to calculate the average shear along EDB. This is E, D, and B. First, let's determine the area of each segment. First, you calculate the area. AB area first. Look back the question. This is your AB, and the area is here. That's the area for your AB, and then you draw. This is point A, and this is point B. The dimension is 40 times 25. This one is from the question. For AB, the question asks you to determine the normal stress, which is a compressive stress. And the normal stress, you know, acting perpendicular. This is your area, and then perpendicular is like this. So I label it as a FAB. How about the direction? I assume. And now the second area is BC. This is BC, and the area for BC is here. And then you draw the BC area. This is point B, this is C. The dimension from the figure 40 and 50. You know that This is the area, and the question asks you to calculate the compressive stress, which is a normal stress which acting perpendicular. So I label it as a FBC. And then EDB. From the question, EDB. This is your area for EDB. Now you draw the EDB area. EDB. E, D, and B. This is your area, and you know that the shear stress acting parallel, so the force should be parallel to the area. So I am naming as a FEDB. Now you have all the area. We calculate the area. Area for AB is equal to, I like to use in meter, it's easier. 0.04 times 0.025 is equal to 1 times 10 power of negative 3 meter square. It is an area. ABC is equal to 0.04 times 0.05 is equal to 2 times 10 power of negative 3 meter square. And area for EDB is equal to 0.04 times 0.075 is equal to 3 times 10 power of negative 3 meter square. Now you have the area. Now we need to calculate the force. FAB, FBC, and also FEDB. First of all, draw the free body diagram. This is from here. I take it this one. You have an applied load of 3000 Newton, and then you have all the forces here. Put back the forces. This one will be FAB, and this one will be FBC. And you know that 3000 applied load is a inclined load. Then resolve it into X and Y direction. By using equilibrium equation, summation Fy is equal to 0, output is positive, then you have FBC minus 3000 4/5 is equal to 0. Then FBC is equal to 2400 Newton. And summation Fx is equal to 0, to the right is positive, then you have FAB minus 3000 times 3 divided by 5 is equal to 0. Then FAB is equal to 1800 Newton. How did I get 4/4 and 3/5? Is from the question. Now you have FAB, FBC. We calculate for shear. Shear EDB. For shear force, you have the force from FAB is equal to 1800 Newton. This is your FEDB. By using the equilibrium equation, summation fx is equal to 0, to the right is positive, then you have FEDB minus 1800 is equal to 0. Then FEDB is equal to 1800 Newton. You have all the forces. Now convert it into stress. Stress AB is equal to FAB divided by area of AB. Stress BC is equal to FBC divided by area of BC. Shear EDB is equal to FEDB divided by area of EDB. You already have all the value. This one, here, here, and also, and then substitute in the equation, then you will get the answer. And the answer for stress should be in megapascal. You will get time 10 power of 6 and then convert it into mega. Mega is 10 power of 6. Please try this example. If P is equal to 15 kN, determine the average shear stress in pin A, B and C. All pins are double shear and each has a diameter of 18 millimeters. Ignore this color. Okay, please do this one. If you convert it into internal forces, FCB, then you can solve this one. AY, AX, then you can calculate. The allowable stress. Many unknown factors that influence the actual stress in a member. A factor of safety is needed to obtain the allowable load. The factor of safety is a ratio of the failure load divided by allowable load. This is the formula. Failure load divided by allowable load, or normal stress, failure normal stress divided by allowable normal stress, or failure shear stress divided by allowable shear stress. You can read this example, and this is the solution. Now let's continue with example. Read the question. The control arm is subjected to axial loading shown in the figure. Determine the nearest required diameter of the steel pin at A and C if the factor of safety for shear is equal to 1.5 and the failure shear stress for steel is 82.5 megapascal. The question already gives to you the factor of safety, which is 1.5, and also failure shear is 82.5 megapascal. First, you have to draw the free body diagram. A and B here is pin connected, so you can make it as a internal forces. This one I label it as a FBA, and at C it's a pin. Pin you have CY and also CX. Now let's solve it. Draw again the free body diagram. You have an inclined load, it is 25, inclined applied load 25 kilonewton and 15 kilonewton applied load, and then you have CY, support reaction, CX, and also internal load of rod AB. The distance. Now let's get the unknown first. You have 3 unknown, then you have 3 equilibrium equation, summation Fy, summation Fx, and also summation moment. I will start with summation moment at C. Summation moment at C is equal to 0. My definition clockwise is positive. Remember that moment is equal to force times distance, which is the perpendicular distance. We take moment at C here, and then we have FBA times distance, which is 0.2. This one will be your F. This is the distance, plus 15 times 0.075. Put the annotation. This is your force and this is your distance. And then you have 25 3/5, the force, and the distance 0.125 is equal to 0. Put the annotation, and then you solve this equation. FBA is equal to negative 15 kilonewton. Negative because we wrongly assume the direction. It should be to the left. And then summation Fy is equal to 0. Upwards is positive. And then you have Cy minus 15 minus 25 times 3/5 is equal to 0, and then Cy is equal to 30 kilonewton. And the last one will be summation Fx is equal to 0. To the right is positive. Then you have Cx plus 25 times 4/5 minus 15. Remember the FBA is equal to 0, and then Cx is equal to negative 5 kilonewton. I put here is negative because I changed the direction. It should be, when you calculate A, you will get 15 kilonewton to the left. That's why it is negative. Now you already have all the internal and also support reactions value. Then we can calculate the diameter. The question asks you to calculate the diameter. You know that factor of safety is equal to failure divided by allowable. Now is in shear. Shear failure divided by allowable shear. Factor of safety is given 1.5. Failure shear is equal to 82.5 megapascal. Now you have to find the allowable. When you want to calculate the diameter, you need to find the allowable shear, not the failure. By substitute the value, then you will have times 82.5 allowable, and then therefore allowable shear is equal to 55 megapascal. Now we will calculate the diameter for pin A. Pin A, from the question, pin A is single and pin C is double. So remember the single and double. This is a single shear. The V is equal to V here at pin A. At pin A, you already calculate the FAB. Remember the internal forces here, FAB. So the V, tau is equal to V divided by area. The V here is actually FBA or FAB. then you know that 55 times 10 power of 6 is equal to 15 times 10 power of 3 divided by area. Then you will get your area. Area is equal to 2.727 times 10 negative 4 meter square. And you know that this is a road, then the formula for area is pi d square over 4 is equal to 2.727 times 10 negative 4, and then manipulate the equation, you will get d is equal to 0.0186 meter, because I use meter. This is for pin A. How about pin B? Same steps. Pin B, you have the allowable, we already calculated. Shear allowable is equal to 55 megapascal. You know that for double shear, it is your V at C. This is V divided by 2, V divided by 2, sorry, not B, pin C. This one you already get from the support reactions, C at CY. Then you need to do the resultant. V at C is equal to 30 and negative 5. Ignore the negative. 30 square plus 5 square and square root, the resultant is equal to 30.414 kilo Newton. Then you have the formula for double shear is equal to tau divided by V over 2A. Shear allowable is equal to 30.414 times 10 power of 3 divided by 2A. You manipulate the equation, then you will get A is equal to 2.765 times 10 negative 4 meter square. Again, pi d square over 4 is equal to 2.765 times 10 negative 4, and then your d is equal to 0.0188 meter. This is your answer for pin A and also pin C. Try this example. This one pin to pin, then you can have the internal forces FCA, FBA. Then this is P is given. And also this one you need to find the P. That's it for chapter 1. Thank you.